So the next topic is on natural weathering, and our speaker is Stefan Reich. Professor Reich studied structural engineering and building management. He worked as a structural engineer for several consultants, was a senior researcher at the Technical University in Dresden, researching fields in structural glass and facades since 2014, professor in structural engineering at Anhalt University of Applied Sciences, and head of the Building Envelope Research Group at that same university. His research focus was on glass and facades. Please welcome, he's all mic'd up and ready to go, Stefan.
Yeah, good morning, everybody. Thank you for your introduction. And I'd like to give you a presentation on a topic, natural weathering of various laminated safety glass with different interlayer materials against UV-induced radiation and the effect of color fading. And I'm here just on behalf of Marius Müller. He's the main author. He was a student at us. He did his master thesis in his historic building constructions, and now he's an architect in an architectural practice, and therefore I'd like to present this topic. And actually the topic is not our idea. Ingo Stelze from Trossi-Fohl came to us and just gave the idea to have a deeper look on a very specialized interlay material and to look how is the effect, how does it react on in a field study, on a long-term study, on colors, on color pigments of different consistency of minerals or organic colors. So that's a picture type, let's say, an idea everybody knows, especially if you have interior carpets, furniture, wallpapers, prints, all these things that fade after a certain time. You know, furniture close to a window fades faster than furniture that is in the back of a room in shadow. Usually the fading has the effect that it brightens. Here's a timber floor. Here's a timber floor and a carpet on this timber floor, and beyond the carpet it keeps its dark color, and just next to the carpet we get a fading, we get a brightness increase. And it's not just the increase of brightness, we also have the effect of a color shifting. Here this was formerly this kind of bluish couch, and we just see the remains of shadowing areas here as well. It kept its original color, and everything else just rapidly changed into gray. I mean, it's a total damage. You can just replace and buy a new couch. And I mean, as long as it is in interior, in furnitures and so on, it is just a risk everybody can bear. So it's something we can afford to replace. But if we go in conservation, if we go on historic building interiors, if you look on old carpets, on old paintings or colors of walls, on old timber floors and so on, then it's not just a question of cost, it's just the question of existency. So is it possible to keep these old items for further time, for next generations? And how do they act, or how do they react against UV light, against natural lighting in exhibitions in old castles or historic buildings where we have certain windows where we sometimes have not the ability just to work with artificial lighting. So let's start with some, I'll switch this off. With some theory. There is basically two main ways that this kind of fading occurs. The first one is the damage of the molecular level by the energy release of a valence electron. That's similar like luminescence or photophorescence happens, that just energy-rich radiation levels up in some electrons, and if they go down to their original state, they release energy. And it can happen that this energy release means we get an increase in temperature, it starts breaking molecular connections and so on. So that causes fading. And the second one is photooxidation. So it's an effect that happens on the surface of the materials and is very UV light driven. And if we go for the principles of the photochemical processes, just quickly say there's several ones. We have a photocleavage process, we have the photodecomposition, photooxidation, and the photosensitization. So it means it's a quite complex chemical situation that leads to fading, and that is almost impossible just to separate it and to split it up into single effects that can be looked separately. How is it possible to assess the change of color, the color spacing between two color points? And the way that is used is the CLAB system. This system was developed in 1967, and it's from the Commission of Illumination. And it's a standard that possesses, it's a 3x system, X, Y, Z axis. It's a little bit difficult here to use this pointer. And the system covers basically the two complement colors, red and green, yellow and blue. And the Z-axis means the brightness. And as more outside we are here in this sphere, the stronger is basically our hue, and saturation increases by going more and more into the center point. That means using this sphere, it allows us to define every color, and then the spacing between two colors is just a linear correlation between the distance, the distance of 2 points in brightness, so Z-axis, in green, red, X-axis, and in blue, yellow, the Y-axis. And it's just nothing than simple mathematics. So, and now the big question is, we have the theory from 50 years ago, and how can we bring a correlation to the human perception? And that's the, let's say, the difficult point. Actually, there is some table we found in a PhD thesis of Feineis. It's a physicist, and in this table we get values of our color spacing. Yeah, that's the color spacing, and the maximum is 127, and from color spacing 1, that's the threshold of the human perception. From this level, we can detect a difference in color. And then, let's say up to 4 here, this spacing will be recognized, let's say, easily, and then from 4, it's something you definitely see from the first view, within a second. That means everything beyond is not of interest in terms of human perception. That means we are dealing in the range of 1 to 4, and that's something we need to consider if we later look on the diagrams, on the results of the testing. In reality, it is not as easy that this CLAB sphere really describes the human perception. In reality, the human eye at first recognizes changes in hue, then in saturation, and further in brightness. And that means it's no linear effect, as we say now, but there is no better system. In reality, the sphere should be anything like a 3D ellipsoid, yeah, so some elliptical 3D structure that maybe could better describe the human perception, but there is no model for this. And so we have to work with this old color space system. Also, if you go back to history and look on further researches, we have two main information. We know that the color spacing, here this color spacing irradiation diagram shows it, is some logarithmic effect. That means it starts very steep, yeah, slope is high, and then the slope gets smaller and smaller. And at the beginning, we need just a small level of radiation to achieve our threshold, yeah, our one color spacing level. And later on, if we have pre-aged samples, then we need, relatively seen, much more further radiation to achieve this change in color again. And then the second one is Harrison damage function. And this function, yeah, it's also so 60, 70 years old, and it consists of a very limited number of experiments, but it says that especially if you go here, this red line is the given border between UV light from here and visible light that's here. And we see that especially light smaller 380 nanometers UV light causes a much higher damage effect compared to visible light that also causes some damage. Yeah, that is basically the second principle. Now let's go to glass. It was, let's say, a quite long introduction. If you go to glass and if you look to the products of Trosifol and see basically how is transmission to our wavelengths situated, then we have, that's just float glass. You see float glass blocks UV light till roughly 290 nanometers. Then there is this called natural UV interlayer, blocks till 300. That's the standard product. Here we have a blocking roughly to the given border between UV and visible light, which is roughly at 380, maybe 375 nanometers. And then there is a product which pushes the blocking range a little bit further into the violet light, which is blocking till 400 nanometers. And the question is, does this extra 20 nanometers help us if we look on conservation issues, if you look on historic building, historic interior elements? The way to investigate by samples wasn't that easy because there is not much standardization available. The best standardization comes from textile industry. They use this called blue wool testing. And blue wool testing, on the right-hand side, you see the original, not exposed part. And here's the exposed part, just as an example. There is 8 levels of light fastening types, and it's for textile production. The standard code, there's also some EN code for this, EN ISO, you see number 105. And they have to check what is the light fastening of their coloring, of their clothes coloring, and how can they put their product into certain light fastening groups. It's an artificial test done by a xenon lamp, and to transfer to reality, it is that the first groups, 1, 2, 3, fade within days, yeah, to up to 2 weeks maybe. And then we have here the last groups, 7, 8, they keep their color of up to 1.5 years of summer sun exposure. Yeah, that's basically the relation between these lab testing and natural lighting. So that's the only standard test we got. And then we were looking on further colors. We were looking on prints. So it's from AGFA. Where is it here? Agfa, the big photo paper company, they produced some paper qualifying tests for their prints. There is an old German code for this, and here you see these prints on our test, our sample carrier. So they use different colors in the red, yellow, green, blue, and violet range. Here you see on the sample the blue wool test stripe, and then we used mineral pigments. They come from a biologic color company called Kreidezeit, it's a German word, who sell their pigments, and it's just pigments on mineral basis for building purposes, mainly facade colors and so on, who have to resist very efficiently against fading. And in total, that's, I think, 18 test samples, and then that's the sun-exposed part, and here this one was shaded, just to include effects from temperature, maybe from moisture, that there is some humidity or something that may affect the test results. We had always these double testing carrier. So in total, we investigated 5 different materials. You see these different interlayer foils of Trosifol, and then further just float glass and a polycarbonate panel. The laminated safety glass consisted of what was a 4.2 material, so 4 millimeters float and 0.76 interlayer foils. And at first we did a double check of the transmission values. And on the left-hand side, it shows these, let's say, standard PVB product, where the transmission or the blocking ended at, let's say, 75, and even below 375 nanometers, there is very, very little transmission, but very, very reduced. And then on the right-hand side, it's this material that brought some extra 20 nanometers blocking, and the blocking ended at roughly 400. So it post-tests to the, or it fit to the product information. That was our test rig. Yeah, it's just a timber box covering 10 glasses, so 2 of each type, and it was perfectly sun exposed to the south, put on a roof, and the test lasted over one entire summer, so 148 days in 2021. And at the beginning, daily measurement was done of the color spacing, and then after a certain time, this daily measurement was elongated to a weekly and a bi-weekly measurement. In total, it was a lot of work. In total, 16,000 measurement values were taken from the samples, and also beside color spacing, we measured humidity, we measured radiation, temperature, and so on. The left diagram just shows the cumulation. Here, this dark line is the cumulative radiation over this summer, and it's almost linear. Then maybe in September it gets a little bit less radiation. And on the right-hand side, especially the upper curve is interesting. That's the interior temperature inside the box, which ended at maximum 55 degrees Celsius. So that's something that is said also for the blue wool standard test that is that is in an okay range. There is no recognized deterioration of color hue at these temperature levels. So 3 examples. How did the test specimen look like after 12 weeks? So the majority, maybe 80% of the sun exposure occurred at these, as we did these photos. And on the left-hand side, it's just this interlayer material that transfers lots of UV light. In the middle, standard PVB. On the right-hand side, it is this plus 20 nanometer interlayer material. Yes, 5 minutes, I get it. And I mean, if you look just at the upper one are the exposed one, the lower one are shaded. You see at the lower ones there is no color change, neither at the blue wool. No, now it's not moving, and no, it moves again. Nor here at these aqua paper test color stripe. And then we see different behavior. We see especially no change in the mineral colors. They kept they kept their color. We see that always the first levels of blue wool shaded maximum in the center, so level 4 or 5. There is some difference. If you look very intensively, there is some difference, and also these paper stripes show some different behavior between the three LSG groups. That is just also an example for a medium stable color pigment. So it's the blue wool level 4. And if you look after 20 weeks, here you see the materials, and after 20 weeks, we get our color spacing, and we get a level of roughly 40 for float glass, that's here and here for the natural UV, and we get a level of roughly 20. Where we are roughly 20 for our standard PVB-interlayer material, and a level of roughly 17 for this plus 20 nanometers, these Trosifol UV extra protect material. So it's maybe in between standard and the extra protect, we have roughly 80% difference, or let's say 20% difference, 80% remaining. And just imagine how does it look like for the human eye, this change in color. The left diagram just shows that our two specimens, two of each sample type, showed the same behavior. We didn't get any distortion by temperature, by humidity or something, so it was almost a perfect line. And now we have three diagrams. At first, we grouped our pigments, our colors, to the group non-stable or less stable, medium stable, and very stable. And this is the group showing the non-stable pigments. And you see some limit here, some plateau at roughly 80 color spacing value. And it achieves this value after 2 or 3 weeks. We see a small difference between, let's say, interlayer materials that block UV light and non-blocking materials, but in between it is such a quick fading that the different materials, the different interlayers have almost no effect. If we go to medium stable, then that's the result where we get the best differences. The upper two lines is float glass and natural UV interlayer. The three remaining lines is the upper one, the standard. Upper one, standard. Oh my God, it's here. That's the standard PVB, and the lower one is these extra protect PVB. And there is a difference in color spacing of 5. That's something we recognize by our human eye. Yeah, that's the level we see easily. And on the right-hand side, it's everything that is very stable, these mineral colors. Within 20 weeks, no significant change of color was observed. That means we get for the non-stable pigments, there is a quick fading, and it doesn't matter. Even the visual light brings enough energy for this fading process. The medium stable elements, they show a significant difference. Here we have a visible effect on the fading, values of 4 to 10 color spacing. And then the very strong elements, they need much more time. 20 weeks is nothing to produce any difference. There is no fading at any material. They are very, very stable because of their inorganic situation. And furthermore, another result is if we are not on complementary colors, but mixed colors, like green consists of yellow and blue, there's a color shifting. That means yellow fades very quickly, blue fades very slowly, and therefore the color changes from green to blue because the yellow diminishes. Yeah, the yellow gets smaller, smaller, and blue remains. And there is also an effect. As better our UV blocking level is, as more we delay this color shifting process. Also in the levels of 5 to 10. And we see this here, that's the color shifting. This line is the standard PVB, the lower line is this extra UV protection PVB, and we have a difference. After 10 weeks is maximum, roughly 10 to 12 color spacing, so very significant, and then it gets smaller after 20 weeks. The fading of the yellow also accelerates at the extra protect interlayer foil. And the summary, it's also in the paper we published. The summary, I just explained it a little bit. Very important is the last point. We have an effect, but the effect is basically always a delaying of the fading. As better, as more UV light we block, we delay this fading further. But for comprehensive results, it is impossible to tell how the human perception effect is, because time and pigment play basically the important role on this. Thank you very much. I'm almost on time.
Thank you very much.